Hi class, how are you today? I think that cheetah wants to join that race. Chapter 7, Estimation. The learning target for today is to be able to compute confidence intervals for mu when sigma is known and compute the sample size to be used for estimating a mean mu. For the scale, you're a 3 if you can compute confidence intervals for mu and sigma for mu when sigma is known and compute the sample size to be used for estimating a mean mu. You're a 2 if you can compute confidence intervals for mu when sigma is known or compute the sample size to be used for estimating a mean mu. You're a 1 if you can find the critical value corresponding to a given confidence level. And you're a 0 if you cannot find the critical value corresponding to a given confidence level. Let's get started. Section 7.1, Estimating mu when sigma is known. Also, there's a duck. Focus points. Explain the meanings of confidence level, error of estimate, and critical value. Find the critical value corresponding to a given confidence level. Compute confidence levels for mu when sigma is known, interpret the results, and compute the sample size to be used for estimating a mean mu. Because of time and money constraints, difficulty in finding population members, and so forth, we usually do not have access to all measurements of an entire population. Instead, we rely on information from a sample. In this section, we develop techniques for estimating the population mean mu using sample data. We assume the population standard deviation sigma is known. Let's begin by listing some basic assumptions used in the development of our formulas for estimating mu when sigma is known. We have assumptions about the random variable x. 1. We have a simple random sample of size n drawn from a population of x values. 2. The value of sigma, the population standard deviation of x, is known. 3. If the x distribution is normal, then our methods work for any sample size n. 4. If x has an unknown distribution, then we require a sample size of n is greater than or equal to 30. However, if the x distribution is distinctly skewed or definitely not mound-shaped, a sample size of 50 or even 100 or higher may be necessary. So it's got to be a simple random sample. We have to know the standard deviation, and either it's got to be normal or it's got to be a high enough sample size. An estimate of a population parameter given by a single number is called a point estimate for that parameter. It will come as no great surprise that we use x bar, the sample mean, as the point estimate for mu, the population mean. A point estimate of a population parameter is an estimate of the parameter using a single number. Even with a large random sample, the value of x bar usually is not exactly equal to the population mean mu. The margin of error is the magnitude of the difference between the sample point estimate and the true population parameter value. So the margin of error is just the difference between mu and x bar in this case. When using x bar as a point estimate for mu, the margin of error is the magnitude of x bar minus mu, or the absolute value of x bar minus mu. We cannot say exactly how close x bar is to mu when sigma is unknown. Therefore, the exact margin of error is unknown when the population parameter is unknown. Of course, mu is usually not known, and there would be no need to estimate it. In this section, we will use the language of probability to give us an idea of the size of the margin of error when we use x bar as a point estimate for mu. First, we need to learn about confidence levels. The reliability of an estimate will be measured by the confidence level. Suppose we want a confidence level of C. Theoretically, we can choose C to be any value between 0 and 1, but usually C is equal to a number such as 0.9, 0.95, or 0.99. 90%, 95%, or 99%, because we want our confidence to be pretty high. In each case, the value z sub c is the number such that the area under the standard normal curve falling between negative z sub c and z sub c is equal to c. The value z sub c is called the critical value for confidence level c. By the way, try saying that 5 times fast. For confidence level c, the critical value z sub c is the number such that the area under the standard normal curve between negative z sub c and z sub c equals c. The area under the normal curve from negative z sub c to z sub c is the probability that the standardized normal variable z lies in that interval. This means that the probability that z is between those two is c. Let us use Table 5 of Appendix 2, or in front of your book, to find a number z sub 0.99. So that's the z-score of 99%, such that 99% of the area is under the standard normal curve, lies between negative 0.99 and z sub 0.99. That is, we will find z sub 0.99 such that the probability that z is between those two is 0.99. We saw how to find the z value when we were given an area between negative z and z. The first thing we did was to find the corresponding area to the left of negative z. If a is the area between negative z and z, then 1 minus a divided by 2 is the area to the left of z. In our case, the area between negative z and z is 0.99. The corresponding area in the left tail is 1 minus 0.99 divided by 2, so 0.005. So this area here is 0.005, as is this area over here, leaving this area in the middle, 0.99, as we've talked about in Chapter 6. Next, we use Table 5 of Appendix 2 to find the z-value corresponding to the left tail area of 0.0050. Table 7.1 shows us an excerpt from Table 5 of Appendix 2. So as you can see, 0.005 would be in between these two. From that table, we see the desired area is exactly halfway between the areas corresponding to z equals negative 2.58 and z equals negative 2.57. Because the two area values are so close together, we use the more conservative z value, negative 2.58, rather than interpolate. So whenever you're not sure, go with the one that ends up essentially hurting you the most, like making you less confident. That way you can be more confident when you get your answer. In fact, z sub 0.99 is about 2.576. However, to do 2 decimal places, we use 2.58 as the critical value for a confidence level of c equals 0.99. We have the probability that z is between those two is 0.99. Optional derivation of equation 1. For a c confidence interval, we know that the probability that z is between negative z sub c and z sub c is c. This statement gives us information about the size of z, but we want information about the size of x bar minus mu. Is there a relationship between z and x bar minus mu? The answer is yes, since by the central limit theorem, x bar has a distribution that is approximately normal, with mean mu and standard deviation sigma divided by the square root of n. We can convert x bar to a standard z-score by using the formula z equals x bar minus mu divided by sigma divided by the square root of n. So the probability that All of that is between negative z sub c, and z sub c is c. So multiplying all parts of the inequality in equation 4 by sigma divided by the square root of n gives us this, that x bar minus mu is between negative z sub c times sigma divided by the square root of n and its positive version. Equation 1 is precisely the equation we set out to derive. The margin of error, or absolute error, using x bar as a point estimate for mu is the absolute value of x bar minus mu. In most practical problems, mu is unknown, so the margin of error is also unknown. However, equation 1 allows us to compute an error tolerance E that serves as a bound on the margin of error. Using a C% level of confidence, we can say that the point estimate x bar differs from the population mean mu by a maximal margin of error. So E equals z sub c times sigma divided by the square root of n. Note, Formula 5 for E is based on the fact that the sampling distribution for x bar is exactly normal, with mean mu and standard deviation sigma divided by the square root of n. This occurs whenever the x distribution is normal with mean mu and standard deviation sigma. If the x distribution is not normal, then according to the central limit theorem, large samples greater than or equal to 30 produce an x bar distribution that is approximately normal with mean mu and standard deviation sigma divided by the square root of n. Using equations 1 and 5, we conclude that the probability that x bar minus mu is between negative e and e is c, our confidence. Equation 6 states that the probability is c that the difference between x bar and mu is no more than the maximal error tolerance e. If we use a little algebra on the inequality, for mu, we can rewrite it in the following mathematically equivalent way. X bar minus e is less than mu is less than x bar plus e. Since formulas 7 and 8 are mathematically equivalent, their probabilities are the same. Therefore, from equation 6, equation 7, and equation 8, we obtain that the probability that mu is between x bar minus e and x bar plus e is c. Equation 9 states that there is a chance c that the interval from x bar minus e to x bar plus e contains the population mean mu. We call this interval a C confidence interval for mu. So we want to know how confident are we that our mean is between these two border points, is within this range. A C confidence interval for mu is an interval computed from sample data in such a way that C is the probability of generating an interval containing the actual value of mu. In other words, C is the proportion of confidence intervals based on random samples of size n that actually contain mu. Procedure: how to find a confidence interval for mu when sigma is known. Requirements: let x be a random variable appropriate to your application. Obtain a simple random sample of size n of x values from which you compute the sample mean x bar. The value of sigma is already known, perhaps from a previous study. If you can assume that x has a normal distribution, then any sample size n will work. If you cannot assume this, then use a sample size n is greater than or equal to 30. Confidence interval for mu when sigma is known. Mu is between x bar minus e and x bar plus e, where x bar is the sample mean of a simple random sample. E is z sub c times sigma divided by the square root of n. C is the confidence level between 0 and 1, and z sub c is the critical value for confidence level C based on the standard normal distribution. Julia enjoys jogging. She has been jogging over a period of several years, during which time her physical condition has remained constantly good. Usually she jogs 2 miles per day. The standard deviation of her times is sigma equals 1.8 minutes. During the past year, Julia has recorded her times to run 2 miles. She has a random sample of 90 of these times. For these 90 times, the mean was ETS bar equals 15.6 minutes. Let mu be the mean jogging time for the entire distribution of Julia's 2-mile running times taken over the past year. Find a 0.95 confidence interval for mu. We have a simple random sample of running times, and the sample size n equals 90 is large enough for the ETS bar distribution to be approximately normal. We also know sigma. It is appropriate to use the normal distribution to compute a confidence interval for mu. To compute E for the 95% confidence interval, ETS bar minus E to ETS bar plus E, we use the fact that Z sub C is 1.96. Using this table here, this is pretty much just taking the values from the front of the book. So 95%, as you can see, is 1.96. Together with values n equals 90 and sigma equals 1.8. Therefore, E is Z sub C times sigma over the square root of n, so 1.96 times 1.8 over the square root of 90, which is about 0.37. Using equation 10, the given value of x, and our computed value for E, we get the 95% confidence interval for mu. ETS bar minus E is less than mu is less than ETS bar plus E. So mu's between 15.6 minus 0.37 and 15.6 plus 0.37. So mu's between 15.23 and 15.97. We conclude with 95% confidence that the interval from 15.23 minutes to 15.97 minutes is one that contains the population mean mu of jogging times for Julia. Sample size for estimating the mean mu. In the design stages of statistical research projects, it is a good idea to decide in advance on the confidence level you wish to use and to select the maximal margin of error you want for your project. How you choose to make these decisions depends on the requirements of the project and the practical nature of the problem. Whatever specifications you make, the next step is to determine the sample size. Solving the formula that gives the maximal margin of error E for n enables us to determine the minimal sample size. How to find the sample size n for estimating mu when sigma is known. Requirements: the distribution of sample means ETS bar is approximately normal. Formula for sample size: n equals Z sub C times sigma divided by E all squared, where E is the specified maximal margin of error, sigma is the population standard deviation, and Z sub C is the critical value from the normal distribution for the desired confidence level C. If n is not a whole number, increase n to the next higher whole number. Note that n is the minimal sample size for a specified confidence level and maximal error of estimate E. A wildlife study is designed to find the mean weight of salmon caught by an Alaskan fishing company. A preliminary study of a random sample of 50 salmon showed S is about 2.15 pounds. So the sample standard deviation is about 2.15 pounds. How large a sample should be taken to be 99% confident that the sample mean ETS bar is within 0.2 pounds of the true mean weight mu? In this problem, Z sub 0.99 is 2.58 and E is 0.2. The preliminary study of 50 fish is large enough to permit a good approximation of sigma by S equals 2.15. Therefore, equation 6 becomes n equals z sub c times sigma all divided by e all squared. So 2.58 times 2.15 divided by 0.2 all squared is 769.2. Note, in determining sample size, any fractional value of n is always rounded to the next higher whole number. We conclude that the sample size of 770 would be large enough to satisfy the specifications. Of course, a sample size larger than 770 also works. So 769, even though that would be rounded to the nearest, is not good enough because it does not exceed what we got of 769.2. So it's got to be one higher to 770. However, anything bigger than 770 also works. And bigger would actually make the margin of error even smaller. But 770 is the least number you would need. Alright, now time for the sponge. For number 1, a sample of 30 former patients at a treatment center for alcohol rehabilitation revealed that the average length of stay was 27.8 days, with a standard deviation of 3.2 days. Estimate with a 95% confidence interval the mean length of stay for all patients at this center. And number 2, suppose X has a mound-shaped distribution with sigma equals 3. Find the minimal sample size required so that for a 95% confidence interval, the maximal margin of error is E equals 0.4. That's it for the lesson. Once again, please make sure to take notes on the entire lesson. Go back to the beginning and rank yourself, take a picture of everything, submit it all to Google Classroom, and have a good night.